Hello, I am very honored to be giving a talk here at the FutureBiotech Winter School. I know we all here love science, but today I'm going to talk about the dark side of science. That's why I have such a low voice, which is thematic to Darth Vader. I'm going to talk about different problems we can experience when reading scientific articles and when trying to do our own research. There are two types of problems which can be in science. One of them is misconduct. There are over 2,000 articles which have been retracted over the years in biomedical sciences because some or plagiarize somebody else's work. But there isn't much to learn from these cases because, well, it's so simple. Don't cheat, don't lie, don't steal other people's work. What I would like to talk about are cases where apparently honest people came to erroneous conclusions which could not have been reproduced by other people. So, as one of the lecturers a few days ago has already talked about, there is a reproducibility crisis in science when people say that they cannot reproduce other people's work. And this has been especially talked about a lot in psychology, but also in medicine, in cancer research, and many different fields. There was a poll done in Nature recently which said that the majority of scientists agree that there is a significant replication crisis and that they have, on their own subjective experience, have encountered cases when they could not reproduce other people's work or even their own work. And that's been in all different fields of science. And so this is something I think we should talk about. So one of the most impactful papers about this topic was done by John Ioannidis, a professor of statistics, in 2005, which is called "Why Most Published Research Research Findings Are False." And I really recommend everyone to read this article because it gives a very good theoretical framework about what I'm going to talk about. I'm not going to go into theoretical details. I'll just give practical examples. So we'll start from what was promised in the name of the study about time-traveling porn. And this is the person who discovered it. His name is Professor Daryl Bem. He is from the Cornell University. And he published an article in Journal Personality and Social Psychology, which is a respectful journal in the field of social psychology, which was called Feeling the Future. And so that's where this time-traveling porn comes into mind. So actually he did 9 experiments. Not all of them were about porn, but one of them was, so that's the funniest one. And in 9 experiments, which he did, 8 of those experiments confirmed that people could somehow feel what's going to happen in the future. So I will give you just one example of the experiments he did. All of the experiments were different in design, but in principle they were about the same idea. So a participant of a study would have a computer in front of him, and he would have 2 screens, one on the left, one on the right, and he would choose on his will either the left screen or the right part of the screen and click on it. And then after that, a computer would use a random generator which does not depend on the input of the user and select also one of the 2 screens. And if the choices of the participant and the computer coincide, then the participant is reviewed with a pornographic photo or image which is much more pornographic than the one presented here. This is a PG version of what could have been there in the study. And so the other decision results in nothing. And so it turns out that you would expect, well, since this is all random, you would expect people to choose a pornographic image in 50% of the cases, but in Bem's experiment, they did that in 53% of the cases. Well, actually, you laughed about 53, but Daryl Bem has a point, which I think is we should give him that point. It's quite honest that, well, if from an evolutionary perspective, the ability to predict the future in 53% of the cases instead of 50 would be a very big advantage. That's the advantage that the casino has over a player in a simple game of roulette. It's actually even less, 2.6%, 52.6% in a regular American roulette is the probability of casino winning, and that's enough for them to make billions of profits. So if you would come into a casino and use this technology, so if you would look at a pornographic image after every time you win, and by that increase your chance of winning, you would beat the casino and you would earn a lot of money. But on the other hand, 53% does sound kind of less, but Darrow Bam has found what every scientist desires to find deeply in his heart. What does this mean or do, Professor? It shows nothing more or less than the most deepest desire of your hearts. And for scientists, it is PUS and 0.05. Yeah, that was what he found. And he found that PUS and 0.05 was present in 8 of the 9 studies that he conducted. So it wouldn't be a surprise for you if I told you that independent scientists had problems reproducing this study. So there were many attempts to reproduce the study. My clicker is also having problems to reproduce the desired, yeah, but will it work in the future? Is there some way to fix this? Okay, please do that, something from my clicker. So the second article there is the largest attempt to reproduce a study based on several thousands of participants with no result. The top study has a very interesting history, so it's 3 failed replications. The authors of that study submitted it to 3 social psychology journals and got rejected on the basis of lack of novelty. Specifically, it was also rejected on the same basis by the same journals that published original Bam's finding. And one more journal rejected it on a review, which was written by Ben himself. And eventually they published it in PLOS ONE, which is an open access journal. So there is a problem of reproducibility here, and there are more studies about this. I'm not going to go into details. The third article about is like a review where the authors discuss the possibility of this being or not being a real phenomena, but they make a very important point that if you look at study how it is designed very similar to that how regular studies in that field are designed. It's not particularly bad. So maybe that means that other studies are also bad, we just don't make fun of them because it doesn't talk about feelings born from the future. So maybe it's a big problem of how studies are done in the field, and we should look into that. I have a new clicker. This is very good. So I would like to talk about what could have gone wrong. And for that, I really like this kind of metaphor. So here you see a target, and there are bullets within this target. And one could assume that this is as a result of a very good sniper shooting quite accurately into the target. But there is an alternative scenario which could explain these findings. It is that there is someone drawing the target to the place where there is the largest concentration of bullets. And the bullets are actually shot randomly all around. And so you just need to draw the target in the correct place. It is called the fallacy of the Texas sniper. And in this metaphor, the data are kind of like the bullets, and the target is kind of like the hypothesis. So if you have some kind of data, you can fish around and find some kind of correlation. Say, hey, this is what I actually thought was true. Doing that in hindsight, it's much easier to confirm something in hindsight. And so, is there some kind of evidence from Bam that he does something like that? Well, there is from Bam himself. He wrote a textbook for PhD students where he says how you should do science, and I'm going to just quote that. The data, examine them from every angle, analyze the sexes separately, make up new composite indexes. If a datum suggests a new hypothesis, try to find additional evidence for it elsewhere in the data. If you see dim traces of interesting patterns, try to reorganize the data to bring them into bolder relief. If there are participants you don't like, or trials, observers, or interviewers who give you anomalous results, drop them temporarily. Go on a fishing expedition for anything interesting. Think of your data set as a jewel. Your task is to cut and polish it, to select the faces, to highlight, and to craft the best setting for it. That sounds like he takes a sniper, but maybe that's not the case in that particular study. We don't know that. But first, I'm going to show you how you can actually prove anything is significant by doing some of this kind of fishing. So this is a great article written by Joseph Simmons and some colleagues about how you do that. So this is an example of a study that could prove, if it wasn't so absurd, that listening to a specific type of music decreases your biological age. So how do you prove that? Well, they took 20 undergraduates. They gave them to listen to randomly to one or two songs, When I'm 64 by the Beatles or Kalimba. Then they asked those people about their date of birth, their father's age. They used the father's age to control for variation in baseline age across participants. And then used an ANCOVA statistical analysis to predict the effect to see what's going on. And according to the birth rates, people who were nearly half a year younger after listening to When I'm 64, rather than Kalimba, and P is 0.04. So this is what you would write in an article if you wanted it to get published, but the black parts of this is what you would have to conceal, not write about it. You don't lie, you just don't tell all of the truth. And the truth was that actually there were more participants, but as soon as they got 20, they said, oh, we got our p-value, so that's good, we're not going to do any more. Then they had actually 3 songs, and they omitted 1 because it didn't give good results. Also, they had many things to adjust to control for baseline age variation, like mother's age, or the answer to the question, are computers complicated machines? And eventually, they ended up with the father's age as the best thing to add to the model to give the predicted result. And finally, if you remove this model, which uses this proxy of father's age from the equation, you get that there's actually no difference. Of course, there is no difference because the baseline age is based on your passport, and your passport did not change during the experiment. So, but you can get this p-value quite easily, and they have shown that you can get that in almost most scenarios by doing an honest study, but just concealing some details. So that's one thing which can happen. And the other thing, which is very important, is the so-called file drawer effect. Here is an explanation of what this is. So suppose you're studying some drug or anything that has some kind of effect. And suppose there is a real effect, which is drawn here. So here on the x-axis we have effect size, and on the y we have sample size. Of course, any study will have some kind of error. You don't get the real effect value. You can get a bit more, you can get a bit less. If you have a small sample size, you'll probably get big errors. If you have a large sample size, you'll have small errors, but they will be probably symmetrical in both directions. You are as likely to overestimate the effect as you are to underestimate the effect. So suppose you're doing a real study and you have a large sample size and you got a new result, you have invested a lot of money, research, you've got a grant for that big sample size. It's unlike you say, okay, we're not going to publish it. So you did a large study, you found nothing, that's probably important. Suppose you got a small sample size, but you got a p less than 0.05. You say, well, the sample size was small, but we still got significant results. So that's not a coincidence. So we've got a discovery here, and you're going to publish it. But if you have a small sample size and you get negative results, you're going to think, well, it's negative results probably because it's a small sample size, right? So who cares? I'm not going to publish that. Or maybe the reviewers are going to say, well, guys, what the hell are you doing here? This does not make sense. There's no novelty here. And you're not going to get that published. And because of that, you get this kind of skew. You get an underrepresentation of small negative findings. But if there are a lot of small negative findings, then your summary of all of the results of a meta-analysis will have an overrated effect size. Let's say it like that. And you will get not the true effect size, but a larger effect size than the one that really is. And now, if you look at the 9 experiments done by BEM, we see that skew. Well, maybe that's a coincidence, but that's funny that we see the exact same skew, the dependency of sample size and effect size, which should usually not exist, unless it's chance, or it's a file drawer effect. Maybe some studies were not reported. There are also 2 other possibilities which could be here, maybe not. One is that suppose you do that trick with an incremental increase of your sample size. So you take 20 participants. Did you get p less than 0.05? No. Okay, let's add 10 more. Did we get it? No. Let's add 10 more. Did we get it? Yes. Let's stop. And if you do it like this, you're going to get this dependency between effect size and sample size. And a third possibility is, suppose in some experiment, a person did not prefer an image that would be shown to him in the future, or a signal that would be shown to him in the future, but actually he avoided a stimulus, maybe because he didn't like that stimulus under your hypothesis, which you're doing with hindsight. You could always explain why you're getting some kind of other effect, but it's still precognition. How can you avoid a signal from the future unless you have precognition, unless you see that future? So if you got a result which is p minus less than 0.05, but it's here, you're avoiding something which you've been shown in the future, you would mirror it to the right, and you would enhance your false positive rate. You would, in your meta-analysis summary, would get a very highly increased positive effect where there is actually none. And so maybe something like this is going on. These are possibilities which we can consider, and we should try to exclude those possibilities when doing our own research. So there is one way which we can deal with this problem is called distinguishing between exploratory studies and direct replications. What's funny is BEM did 9 studies, all of them are different. None of them is a direct replication of one of his studies. He could have done the same study 9 times, and if it confirmed 9 times out of 9, 8 or 8 times out of 9 times, he would get the Nobel Prize, I think. But he did 9 different studies. So you need to do direct replications. You already have your hypothesis. You've drawn your target, and now you shoot bullets and see if you can hit it actually or not. In medicine, this was countered by this initiative such as clinicaltrials.gov. So if you want to have your study considered by the FDA, for example, you first pre-register it. You tell everybody what you're going to do, how you're going to do it, and how you're going to measure the outcomes. So you've drawn your target, now you do the study. And then you're not required to publish your results, unfortunately. There is no legal punishment for that, but at least other scientists can now have a look at how many articles have went into the file drawer. And as a case example, I present to you homeopathy. If you go to clinicaltrials.gov and add the keyword homeopathy and you look for the completed trials, you will find there are 62 completed trials of homeopathy. If you look which of those studies have results, you will find that 11 of those studies have results. And 51 of those studies do not have published results. Well, you can only hypothesize what went wrong with those studies or why they did not decide to publish the data on clinicaltrials.gov. But it shows you like how this could lead to an incorrect conclusion if you try to justify some kind of decision on your attributing some effect to a particular medicine. And this is homeopathy, okay, that's not really discussable, but let's go to something that's real medicine, like Tamiflu. And this is a very recent story about how the World Health Organization downgraded oseltamivir or Tamiflu from the list of essential medication. And this happened due to a very simple fact, due to this file drawer effect, when at some point the pharmaceutical companies presented evidence that oseltamivir is very good, it's great, and you should like all use it. Well, I'm exaggerating, but you get the point. And so based on that data, UK stockpiled Tamiflu, and so did the US and other countries, and will added it to the list of essential medications. But then it turned out that the pharmaceutical companies reported only a part of all of the studies that they did, and it took many years for many people, for many activists and scientists to get the whole data set. And when the whole data set was meta-analyzed, it showed that, oh, it appeared that Tamiflu does work. It does reduce the time of symptoms of flu, but a much less extent than it was originally claimed. It also has side effects, and it also does not reduce the rate of hospitalization and mortality, which is the most important reason for why you should have the drug prescribed to like almost everybody with flu. So it makes much less sense now. And so after the complete data set was reviewed, they said, okay, we're going to remove it from the essential list of medicine. So it coincided with Tamiflu getting the first generics. So it didn't actually help much here, but it was too late with that decision. But at least we got it now. And as a joke on all this stuff about publishing positive results and not publishing negative results, there's a great satire written by Irina Bones in a peer-reviewed journal, which she noticed that 97% of articles across a random section of psychological journals are positive results. And so when Daryl Bem discovered precognition, he actually discovered something already known in the field of science. There's a much more stronger effect. Psychologists, they know in advance which hypotheses are correct. You don't really need to do any studies. You just make up a hypothesis, and it's correct with p less than 0.05. Just that's the evidence here. You can see 97% of the hypotheses come true. Well, of course, that's a joke, but it shows the problem of the file drawer effect. We don't know how many negative studies with negative results are there, and that's a problem. So back to the p-value thing, we should discuss why that's a problem as well. And that's a problem because it gets misinterpreted a lot of times. So p-value is you have some kind of statistical model. You have a null hypothesis that it's all random. There is no correlation, no effect, nothing's going on. Everything is random, and you get some kind of statistical summary based on your data, and you can say that the probability of obtaining an effect size of the statistic of the magnitude you observe or of a larger magnitude is less than this p value. I mean, if you calculate the probability that the observed effects are of okay, my English got me confused here, but you can read the definition here on top. The probability of obtaining results of a larger or the same kind of magnitude by chance. There are many problems with p-value because people usually think about it as like, okay, we got p less than 0.05. That means that we are 95% confident in our results. It means that there's only 5% chance of coincidence, so it's probably true. Actually, in most cases, it's not like that. It's probably not true in most cases. So let's have a specific example. Suppose you have a test for a disease, which is quite accurate. It has a 96% accuracy in terms that has both 96% specificity and sensitivity. 96% of your patients who are sick, who are really sick, will be classified as sick. 96% of who are healthy will be classified as healthy. Well, that's quite good. But suppose the disease is present in only 1% of the population. So among 100,000 subjects, you will have, well, 1,000 people with a disease, 99,000 who are healthy. And among those 1,000 with a disease, the majority will be true positive and just a little bit of false negative. Among 99,000 of healthy people, you have 95,000 of true negative and a little bit 4,000 of false positive. And suppose you're testing a particular person chosen randomly from the population, and he has a positive test, and that's the chance of coincidence, the chance of a test failing is less than 5%. But if you want to calculate the probability that he is actually sick, you have to calculate the conditional probability, considering the initial low prior probability of the person having a disease, which is 1%. So basically, to calculate this probability, you notice that the amount of true positives is very small among all of the positives. All of the positives is the sum of these two types of samples. And so if you do the simple math, you get that with 80% chance that person is healthy despite having a test saying that he is positive of the disease. So you shouldn't probably right from the start treat him with some dangerous therapy that might kill him. You might consider doing a second test to reconfirm your finding, to be more confident that this person really is sick. And the same thing goes with p-values in studies. So if you have, say, a study that says homeopathy works p less than 0.05, you might measure the probability of homeopathy being a thing in a world where we have physics and chemistry and atoms and molecules which are diluted to, well, if there are no molecules, there's nothing to work there, and the probability of being a false positive, and the false positive is quite probable in this scenario. So another thing with statistical analysis is the problem of multiple comparisons, which was brilliantly illustrated by this XKCD comic. So you have these two scientists, and they are checking whether or not candy jelly beans of different colors can cause acne. And so they checked purple jelly beans, and they got P is larger than 0.05, so it's not significant. Then they checked brown, then they checked red, blue, yellow, and etc. And they did 20 tests, and out of those, only the green jelly beans turned out to be somehow linked to acne with P less than 0.05. And so they write a paper, they forget about the other 19 negative tests, and they say green jelly beans are linked to acne, 95% confidence, only 5% chance of coincidence. But if you run this kind of type of experiment like 100 times, in most cases, you will get this false positive result just from coincidence. And that's a problem. You should account for multiple comparisons. How to do it? There is a Wikipedia page. I'm not going to go into that details right now. This problem was illustrated brilliantly as well by Craig Dennett, who noticed that in some studies on neuroimaging, you get this problem that since there are very many regions of the brain for which you can measure some kind of signal of the brain activity, there are many voxels in the MRI which are being analyzed simultaneously. If you look at a specific only one voxel, you can get a false positive result just because there are so many voxels you can look at. And to illustrate this problem, he did the following. He took a fish, He put it into an MRI and he showed to that fish different pictures of people in different situations, and he found that there is a region in that fish's brain that can be that specifically reacts to certain situations of people on those photos. And the fact was that the punchline was that the fish was actually dead, and so it shouldn't have any brain activity at all. But there is noise in the MRI readings, and if you ignore this multiple comparison problem, in some voxels you will get a POS and 0.05, and you will say that, yeah, we found brain activity that's different in between two scenarios. A little bit of astrology to add to the mix. So this is from a researcher. It is a story quite long ago in a galaxy far, far away, when Michael Gauquelin, a researcher of astrology, he discovered what was called the Mars effect. So he looked at the birth dates of eminent athletes, and he found that if you look at their birth dates, you will notice that the planet Mars, for some reason, is overrepresented in two sectors of the sky. So astrologers, they divide the sky into 12 sectors, and Mars were overrepresented in two of these sectors during the birth of these athletes. And he said, so Mars, if you have Mars in a specific spot of the sky, it makes you like a better sportsman. That would be a good evidence. That would be good evidence for astrology. But there was a problem, the same problem of multiple comparisons. There are 12 sectors in the sky. There are 12 times 11 combinations of two sectors, and there are 10 planets considered in astrology. So the Sun is also a planet, the Moon is a planet, and Pluto is a planet, and it sums up to 10 planets in astrology. And if you do that correctly, so Gauquelin got this p-value, POS in 0.00005, that's impressive. But if you take into account that you can choose among many different planets and combinations of two sectors, and you do this kind of Monte Carlo simulation, you take the same sample size, you randomly put the planets into different sectors, and that's what I did for this journal called Skeptic Magazine. And if you do that, you get that Gauquelin's result is actually quite statistically normal. It's what you would expect to get, and the p-value is not 0.05, it's actually like that. That's the probability of getting some kind of effect of some kind of planet for some kind of two sectors. And that basically explains away this astrological claim. Now, the same thing's going on in articles, some articles claiming that GMOs are bad for you. And this is a review, a critical review we published with my colleague, Alexander Tuzhikov, also from the Faculty of Bioengineering and Bioinformatics. So we looked into 5 studies, which were the most eminent studies, where everybody cites those studies when they say GMOs are bad for you, to look for how did they do the statistical analysis. So one study didn't do statistical analysis at all. So they said, look, here is more, so it's bad. Actually, if you do statistical analysis, there is no, like, it's not significant even with p less than 0.05. Now, for other studies, they had the multiple comparison problem. Just for example, you take a sample of 10 rats in the control group, 10 rats in the experimental group, and you look for the expression of several thousand genes, and you find out that for several of those genes, several tens of those genes, there is a p less than, say, 0.001. And so what? You have 2,000 genes, so you're doing 2,000 multiple comparisons. So you're obviously going to get some false positive results. How do you account for that? Do you try to do a replication of that? No, you don't. You just say GMOs are bad. And that was the problem with those studies. Switching from statistics to the experimental design, this is a very important case of Jacques Benveniste, who got an article published in Nature some time ago, actually a long time ago, but is still, this research still echoes for the same day today. So what he did is he took antibodies to immunoglobulin E, and he diluted them homeopathically to a state where there are no molecules present, and he added those antibodies, those molecules, well, that substance, that let's call it homeopathic water. He added this homeopathic water to human basophils, and they had a signal which was different from when you add regular water, control water, to those basophils. And so he said that the water remembers those molecules which were previously in it, and that was like the discovery of water having memory. And So he got 2 Nobel Prizes, one for discovering that water is a smart molecule, it has memory, and another one later for discovering that this memory can be transferred through the internet or the phone wires. This is actually being still researched in Russia. In Moscow State University, there is a group of people who they can send you digital drugs. You go to their site and they send you a drug through the internet. You download it and you write it down on your compact disc, and you put a glass of water on top, and then you drink the water and you get cured from almost anything. So I'm not going to discuss this case because it was never published in a normal peer-reviewed journal, but this was, and it was published with a comment from the editor that this is actually kind of weird because it kind of defies the laws of chemistry and physics. So we should look into it more carefully. And John Maddox, who was the editor of Nature at those times, with 2 skeptics, they went to Benveniste lab and they noticed that the study is not blinded. So the experimenters, they know where they have the homeopathic water, where they have the regular water, and maybe that could influence the result. So they developed a blinding protocol. They tested the same study once. They replicated the study, and they found that it does not replicate under blinding conditions. And so it was also published in Nature that this doesn't work. And after that, there were over a dozen of the same kind of studies. And every time it was done blinded, they got no results. Every time they did it non-blinded, or sometimes they got positive results, sometimes they did not. So that's like a psychological phenomenon, not a physical phenomenon. It's a memory of water. And today, this still is going on. This idea that you dilute molecules and it's going to help somebody. It's been published in all of these journals in a new form, because homeopathy is already this kind of a bad word. You shouldn't use it if you want your article to be published in some kind of journal with an impact factor. But maybe you could change the word and say, call it not homeopathy, but release active drugs. That's how Oleg Epstein, CEO of a company called Materia Medica, rebranded his product. It was initially called homeopathy, then he changed the wording, so it's now release active forms of antibodies. So how is this? What is the principle that he uses? So you take some kind of molecule which has a science name, a good scientific sounding name, like enosyntase, insulin receptor, interferon gamma. You get antibodies to that, and then you dilute those antibodies to the power of 10 to minus 26, or 10 to the power of minus 400 in some drugs, and you can cure diabetes, impotency, encephalitis, influenza, well, basically anything. And how do you get those articles published? Well, you just don't use the word homeopathy. You just say, like, we are testing normal drugs, and somewhere in a small fine print, you say how they were prepared, diluted. You also conceal your conflict of interest. You don't do randomization. You don't do blinding. And so you get some kind of strange result, and you preferably publish it in open access journals, which ask money from you, and you give them money, and they publish your stuff. Not all of these journals are open access. Drug Discovery Today is a very respectable journal. It published a review of insulin receptors, and the review was written by normal guys who do science on insulin receptors. They have normal studies. So, but they got funding from Materia Medica. They added Epstein to their co-authors, and they added one paragraph quoting those studies about the homeopathically diluted antibodies to insulin receptors that can cure diabetes. And that got published, and so now they have an article in a review. So me and my colleague, we tried to write to the editors of 5 of these journals and say, guys, what are you publishing? Look, here are the errors in your studies. What you gonna do about it? So one journal, this one, they just did not respond. 3 journals, they said, okay, we're gonna look into it, and several months have passed and they did not look into it. And one journal, Medical Virology, they published our criticism after peer review. So the reviewer said, oops, we got that published, sorry, they should probably say something about it. But this also is not a victory, because basically the authors got to reply, and they replied not to our criticism, but they just said, guys, this is not homeopathy, this is really active forms. Look, we have 20 studies, we are citing them all, we increase our index here by 1. That's how we roll in modern science. And this is just for you to, appreciate the absurdity of this. This is some quotes from some of the articles by Oleg Epstein. The genetic code of an individual is not just the primary nucleotide sequence, but a unique and whole Holographic spatial organization that holds its own set of subtle supramolecular oscillatory characteristics. Technologically processed dilutions also exert activity when they do not contain molecules of parent substance. So that's proven now by scientific journals all over the continent. I think it's great. So Karl Popper, a famous philosopher of science, he is famous for the falsification principle, the idea that scientific hypotheses and theories should in principle be refutable. I also had a very good idea about how science can be compared to an evolutionary process. There was an article called Evolutionary Epistemology. And in that article, he says the following, that, well, in evolution, you have this survival of the fittest, and in science, we have the survival of the fittest hypothesis. Hypotheses need to survive the criticism of scientists who try to reproduce, to deconfirm, to show that something is wrong. And those hypotheses that survive, they kind of live on, and they give some offspring in the future. Well, it's kind of a metaphor, but I really like it. I think this is not just about scientific facts, but it's also about the scientific method itself. We can learn on these errors in order to improve the methods that we are using. And if we don't do that, we continue producing irreproducible results and different kind of pseudoscience. So an example of science correcting itself is this case of an article published in Nature. So this is Xena turbella, and this article claimed that Xena turbella is a mollusk because they did a DNA analysis, and so it confirmed it's a mollusk. But then later it turned out that Xena turbella is a deuterostome who eats mollusks, and that's why it has mollusk DNA somewhere in its insides, and that's why you got a wrong conclusion. And so you need to account for contamination of DNA when you're trying to do DNA analysis. Now, as these guys did everything correctly, they found an error, corrected the error, that's good. Now, once I got another DNA study where guys said we found the genome of Yeti, of Bigfoot, of Sasquatch. And so they presented a DNA analysis. So that was, if it was really, you know, a Yeti and some relative human, I would be really impressed. But unfortunately, it was just a mixture of human sequences and sequences of someone who I identified as a reviewer as being probably a bear. And they were kind of like misassembled together. And it was like somebody put his finger into a pile of bear poop, and then he sequenced that, and then he misassembled it and tried to publish. And so I wrote like a detailed explanation why it's probably wrong. The authors decided that it's not convincing, so they, but since the journal rejected the paper, they just bought their own journal and published it there. There's one article in this journal called De Nova, and you can download the paper for 20 bucks and read it yourself. Or you could read a review in the Proceedings of Royal Society, which says, well, actually, there are like a lot of guys who did DNA analysis of Bigfoot, and in every single case, it's a contamination problem. They just don't care about the issue, and that's why they get these results. Homeopathy, let's go back to it. We are actually, should say thank you to homeopathy because it led to the discovery of the double-blind, randomized experimental procedures that we use today for normal medicine. The first randomized double-blind trial, the so-called Nuremberg Salt trials, or tests, were conducted in 1835 by Friedrich Wilhelm von Hoven. They got a negative result. It did not show that homeopathy is different from homeopathic water, but that was a discovery of a very important novel method because it gives you more accurate results than just relying on your own senses and expertise. And when you apply the same method to other medical procedures, you find that something which is considered good is no longer considered good. This is like a very dramatic example. So they decided that you can actually do sham surgery and compare surgery to sham surgery to have like a placebo surgery. You just, you know, make a slit and then you sew it back, and the patient thinks he had surgery, but he really didn't. And when he did this kind of study on a particular type of surgery, which was performed 700,000 times per year in the US for the cost of $4 billion of money, it turned out it doesn't work. And that was like an important discovery in the field of medical science. And so the final topic which I wanted to bring to your attention is also from the field of medicine. It is a very good study that explains a lot about why we have so much alternative medicine and why it's so popular. So these guys, they did the following experiment. They had people with asthma, and they gave each person 4 kinds of treatment in a randomized order. So it's a different kind of randomization. So you get all 4 treatments, but the order is randomized. And there were 4 types of treatments. One was an actual drug against asthma, which you inhale through an inhaler. There is a placebo treatment, a placebo inhaler, which is not different in terms of, it looks similar as a regular inhaler. There was sham acupuncture. So it was like acupuncture, you put needles in your skin, but they did it specifically incorrectly, so that even those who believe in acupuncture don't say that, oh, it works. And finally, there was a no intervention control, so they did nothing for the time period. And after each session of each treatment period, they did measure 2 outcomes. One outcome was you can really measure how has the breathing of a person with asthma improved using a respirometer. So a person blows into a tube and you measure how is the ventilation working, what is the volume of the air he can produce through a period of time. And the other way is you ask the person, well, did you get better during this period? How do you think? Did this treatment work? And when you look at the actual treatment, you see that it's much superior to all of the other kind of placebo interventions and non-interventions. This doesn't work. It doesn't change anything. Wishful thinking does not help you cure asthma. But drug does. Now, if you ask the people, everything works, except for the non-treatment, comparing to the non-treatment. And people can discern what works and what does not, simply because it's very difficult. It's counterintuitive. Science is counterintuitive. And because of that, doctors and patients, they try to make decisions based on some kind of subjective feeling, oh, this is helping me, but they come to erroneous conclusions and start believing in homeopathy, acupuncture, and other kinds of stuff. And one thing which has become very popular even within the scientific community is so-called evidence-based meditation. And when you look at that and consider the lessons learned from this particular study, you find something very interesting. So this is a review published in 2014, and they looked at all of this evidence-based meditation studies, and they found that only 3% of the trials ever performed in this field have had an active control. So 97% of the studies are comparing to no intervention. So how can you actually measure whether it works or not if you're not having a proper control? And so you understand, you can't do a proper double-blind randomized study because the person knows whether or not he's meditating, but at least have an active control. And when you look at the active controls, you find that there's actually a very weak evidence, or similar to none, that meditation is better than, say, another kind of relaxation. You could just, play some music. You can just, talk with a friend, whatever you call an active treatment. So I think that this is not like a definite, verdict, like, okay, this doesn't work or something like that. This is just something every one of us should take into consideration. That science is difficult. It's counterintuitive. There are many pitfalls. And maybe there are some pitfalls which we don't even know about today. Maybe we'll find out about them later. And we can improve ourselves and how we do science by learning from mistakes of others. And that's how we're going to make science great again. Thank you.
Are there any questions?
Thank you for interesting talk and hot topic. I agree that there are many examples of really strange articles and so different examples you have told for us. But I believe that different scientists, they are really good guys, and they know statistics, know mathematics, and they don't want to publish false. But there is, I think, really a big problem of nowadays that science is like a competition, like a business today, and in the field of money, grants, in the field of time, yes, because you should be the first to publish your data, and if you are not in trend, you will not thrive. Yeah. And how do you think scientific society can solve this problem?
Yeah, I think that's a very, very good question. You're actually like striking to the heart of the problem, because this idea of publish or perish, which is persisting in the scientific community, where novel results are much more preferable than good results, than reproducible results, when sensations are being positively feedbacked, like some institutions actually, they encourage articles to be like to get high outmetric scores. There's now not just Hirsch indexes, but outmetric scores. We just measure how many times the news outlets have quoted your study. And of course, news outlets will really like to quote a study that says GMOs are bad, homeopathy has been finally discovered to work, or something like that. So there is no like simple solution to this, because this is embedded in the culture of how this system works. I could say, let's crash the system, but I don't have a good solution to the problem. Maybe we just need to raise awareness of these problems, so that as maybe when a critical mass of people starts thinking about this, then you have some possibility to change the way we do it. Because people, well, we are all in some sort of like conformists. We look at how other people evaluate our work. And as soon as scientists start evaluating other scientists' work based on how good the study was done, and not by just, oh, you got an article in a very good journal, but it's bullshit. But still, it's a good journal, so I respect you. Well, we are part of the problem, so we need to change our own attitude to this. But I know this is just like words. It's not a real solution. People have suggested that we need to stimulate replication studies. There have been ideas that we need to, there was this famous reproducibility project, which attempted to reproduce many studies, and they actually found that many studies can't be reproduced. So I think governments should be interested in providing funding to replication of different studies. I think that there should be more openness to discussion of scientific discoveries. For example, while those journals have refused to acknowledge the criticism that we did publish the criticism on PubPeer. We published it on PubMed Commons. We published it in PLOS ONE in the comments section. So, and maybe other scientists can do that as well. If you find a bad study, you see it has a flaw, go and write a criticism on PubPeer, write a criticism on PubMed Commons. Don't say like, these guys are bad, they're evil, and they're doing bad science. Just say, guys, you have an error, here's the error, just the facts. So maybe that could also help.
You've mentioned that maybe government has to spend more money on reproducible science, but because, we live in Russia, maybe there should be legislation that covers fraud science, because money is very expensive. Maybe we just should ban or maybe send to jail.
For bad science?
Yeah, for fraud science.
Fraud science. Well, you see, that's the problem. How do you prove that it is fraud science and not a rookie mistake? How do you prove that this person is, well, okay, in some cases, you can show, for example, that a person has a conflict of interest and he does not disclose it, like in some cases of that Materia Medica articles. Actually, well, they can always say, oh, we forgot, and should you send someone to jail because he forgot? And maybe in some cases, you will find someone who forgot to disclose some kind of conflict of interest. So it's like a tricky situation. I don't know. I don't think you should put scientists into jail, but maybe you should not fund them. And maybe you should not allow the drugs, like the ones produced by Materia Medica, to be available over the counter when they have no real evidence of that they are working. If you judge it by the merits of modern medicine.
Thank you for the lecture. What do you think about open access journals? Isn't it a conflict of interest, and should we ignore publications in such journals?
I think that well, okay, this is a hard question, because from one thing, open access has its own merits. For example, the openness of an article allows many people to read it and find and criticize it and to read it, and if you actually look at cases when bad science was published, it's not just open access journals. So you can also find very different bad and unreproducible research in regular journals as well. So I don't have a final answer on this. I think this is a topic that needs to be investigated. I think that, well, no, I have not done the correct research to comment on whether or not open access journals are much worse than their regular competitors. In terms of publishing fraud science or pseudoscience or just non-reproducible results. There are many good articles published in open access journals.
And there is a need.
Some of them, yes. So it's very difficult to make an overall statement about the whole thing. So maybe the correct answer would be like judge a journal on its own merits. Yeah, maybe that's something we can agree on.
And is there a need of such great amount of different journals? Among them, there are journals with nil impact factor. Do you think we should avoid the journals and only Nature and other
no, not only Nature,
good
but,
journals?
Yeah, well, while we had a discussion with some of the other lecturers down in the bar a day ago, and one of them commented that it is actually one of the problems is that you consider that a very high-ranking journal is much better than a normal impact factor journal. Like, so for example, if you take some journal like Cell, it's it's a high impact journal. Let's say, I don't know, some medium journal, okay, has an impact factor, say, of 4, 5, 6, something like that. Yeah, they can also have a similar rate of high quality papers in it. But when a journal has impact factor 0 and it's actually not indexed by anybody, it's probably a bad journal. or new. Okay, that's a good.
Okay. So thank you for a brilliant talk. And what's your opinion about? I don't know the correct name in English, but the journals when you fix the design of the study priorly, you fix the statistical methods. The journal gives you okay to publish this study, and then you perform study and you publish any result, negative or positive. So you just fix your study design before you start to do this, and then you will have no bias, no this bias in facts. I know that there are some kind of these kind of journals in psychology. And did you heard about this kind of journals in biology? And what do you think about this type?
I know one journal, I think it's called Clinical Trials or something like that, a journal in medicine, which publishes designs of clinical trials someone is going to perform. It's like independent from clinicaltrials.gov, but it's like an academic journal that publishes trial protocols.
Yeah.
In biology, I don't know. Does anybody know here? There are a lot of scientists here. Okay. Oh, you know. Okay. I hope everybody knows what we're talking about. So no, I don't know. I think it's a good idea. I think that some respectable scientists, a group of respectable biologists, decided to create such a journal with such rules, I think that would be a very good idea. Maybe eventually it could receive the respectability of the high-ranking journals that we have today. I think that would be an important thing on this issue.
Okay. I'm sorry. What do you think? Should journals publish for not false, negative results? So as not to replicate the same false in design of investigations.
Yeah, I think that it would be great if journals started publishing negative results. First of all, sometimes negative results are required after a very large amount of work. So I think that somebody's PhD thesis could be a negative result. So, for example, we had, as long as somebody makes a sound hypothesis, right, which makes sense, so somebody should check that hypothesis. And so, suppose a person is doing a lot of research and finds that this doesn't work. So, if he doesn't publish it, maybe this will not stop 100 other people from trying to do the same thing and wasting their time. And now, if you get a negative result and it's published, and it's great. And there's actually a journal called, I think it's called Journal of Negative Results or something like that. It's not very impactful, but it's a great idea. And I think that, so remember the name. So next time you get a negative result, why don't you go publish in Journal of Negative Results? So I think that's a very, very important thing to do.
But don't you think that the problem is more fundamental than this? For example, like in arts and literature, they recognize like that, like postmodernism, that like people have their own perception of things, and science is also a product of human brain, of human imagination. So maybe the problem is more fundamental. Like,
okay, I really like this quote by Tim Minchin, an Australian musician, who said, I am not very good at quoting, so he has a poem called Storm, and there is a line something like this. So, do you consider the subjectivity of the objective world when you're deciding whether to get out of your house from the door or the window on the second floor? So there are objective truths, and science is about finding how the world really is. And while there are social things that do influence science, so scientists are also people. Scientists, they need to get money, they need to feed their families, and so they can be tempted by grants and this publish or perish system. They may have ambitions, so they want to publish specifically in Nature at all costs, even if they're not sure about whether the data is correct. But that is considered something bad. At least I hope it is considered as something bad, something we should fight against. We should try. Yeah, sometimes we cannot exclude the subjective part of the science, but we're trying to do that. We're trying to do double-blind studies instead of just doing, oh, homeopathy helped my mom, so that probably it works. So that's the difference. The difference is in one case, you're trying to eliminate subjectivity as much as you can, and in other cases where you embrace subjectivity and say, my opinion is as good as anything. So if I say the world is flat, it's as good as the opinion of a scientist who says it's actually not flat. And I think that's the wrong thing to do. And those guys who are postmodernists who talk this kind of stuff, I think they're fundamentally wrong and doing a bad job for all of us.
thank you for such an interesting lecture. I'm afraid that my question could be something like shame on me, but could you please comment on what you called on what you call multiple comparisons? Because as far as I know, multiple comparisons is a term that used when you compare few groups. So when you were talking about a saying of evaluation of hundreds of genes or thousands of genes, that is different experiments. It's not comparison in. So please comment on that.
Okay, I understand what you're saying. Well, probably is the best example would be in the field. This problem was recognized really early in the field of genome-wide association studies. So you have a lot of SNPs on your chip, and you have patients, and you have people who just are healthy. And so you consider that, or suppose that the SNPs are independent from each other. Actually, it's not always, not really the case, but let's suppose that independence. So you have a sample size of some people who are sick, some people who are healthy. You do this SNP analysis, and then you find some statistically significant differences between the samples. And so the problem, which was addressed by the scientific community a long time ago in this field. Everybody like knows about it in the glass industry. Is that you will get false positives because there is since you have like thousands or hundreds of thousands of SNPs being analyzed simultaneously, some of them, even if there is no genetic component to this disease, some of them will be unevenly distributed between the groups. And so what they do is they do the following. One is you can do what they call the FDR correction. It is when you say, okay, it's okay for me to have, say, 5% of erroneous false positive conclusions, and you look at the topest hits, which are the most unevenly represented between the sample and the experiment and control groups, and you take those and you apply higher confidence to them, and you say that all other p-values are bullshit. And the other approach is you do basically the most correct thing. You take the best hits you got, and you do a direct replication. You take an independent sample. You take, suppose you have like 2 best candidates of SNPs because they are unevenly distributed between the sample, the control and experimental group. And suppose they are missense mutations, SNPs which could be really linked to some kind of problem of some protein not working properly. So you take your best candidate. So that's your best guess what could be wrong with these patients genetically. And then you take an independent sample of patients and control group, and you just check this 1 or 2 or 3 or 10, but much smaller amount of hypothesis to reconfirm. And if you do that, there is a much smaller chance of you getting a false positive. So multiple comparisons applies to this situation in the same sense as it applies to any attempt to test multiple independent hypotheses.
Yeah, thank you. I understand now. There was a little misunderstanding because I did not get that you are talking about simultaneous experiments. So
yeah,
because if you have like some independent samples and you will measure one SNP and one SNP and second. Sorry, I'm not really a specialist in genome-wide studies. I was thinking about like PCR analysis for transcriptome, for example. And if you have different samples and you measure one gene, and when you one transcript, and when you will measure second transcript, this will be okay. Or maybe we should talk about it.
Maybe we should talk later because my answer would depend on how you design your study. So
I think
depending
that
on your
will
study
be
design, you may or may not encounter this problem.
I think that will be the great topic for the discussion during the dinner.
Okay.
And let's thank Alexander one more.
Thank you.